All right, welcome back everyone to AI Paper Podcasts. Today we're going to dig into a really interesting paper called Latent Diffusion Planning for Imitation Learning. Anyone working in robotics or imitation learning knows this big challenge. You need loads of perfect expert demonstrations. It's a real bottleneck. This paper offers, well, a potentially quite clever way around that.
Yeah, exactly. So for the quick summary up front, the core idea is this thing called Latent Diffusion Planning, or LDP. Basically, it splits the problem. It separates figuring out what future states you want to reach, that's the planning part, from figuring out how to actually make the robot move to get there, that's the action prediction. And the key thing, both of these parts work in a learned, kind of compressed latent space. They use diffusion models for this. This structure lets LDP learn from all sorts of data, not just perfect expert demos. Think action-free video or even like failed attempts.
Action-free video, so just watching the task happen.
Exactly,
Yeah.
or suboptimal stuff. And because it can use this other data, it performs better, especially when you don't have much of that perfect, expensive expert data. The main components, are a visual encoder to understand the scene, the latent planner for future states, and then an inverse dynamics model to get the actions out. That's the gist in like 60 seconds.
Okay, that's a great overview. Let's unpack that. Because for years, the standard playbook for teaching a robot, say, a tricky pick-and-place task was just record a human doing it perfectly, over and over.
Hundreds, maybe thousands of times, yeah.
And I mean, anyone who's actually tried to get a robot to do something complex knows it's got problems.
Oh, absolutely. It's incredibly time-consuming, for one, super expensive. But beyond that, it's just not very robust, right? The real world is messy. What happens when the lighting changes slightly or the object is in a slightly different spot than in those perfect demos?
The robot just gets confused.
Often, yeah. Existing methods can be brittle. And think about all the data we usually just toss out. The failed attempts, the setup movements, maybe just videos of the scene.
Right, data that could be useful, but traditional imitation learning often just ignores it because it's not labeled perfectly with expert actions.
Precisely. And that's the gap this paper LDP tries to fill. How can we leverage all that other readily available but maybe imperfect data?
It's like learning tennis just by watching Wimbledon finals. You miss all the practice drills, the common mistakes people make.
Exactly. You miss the process, the learning from errors. So LDP's approach is different. It's modular.
Okay, modular. You mentioned separating planning and action prediction. Let's dive into that.
Right. So the planner figures out a sequence of future states. What should the scene look like a fraction of a second from now, then the next fraction, and so on. And then separately, the inverse dynamics model, the IDM, looks at two consecutive planned states and figures out the action needed to get from the first to the second.
And this all happens in that latent space you mentioned, not directly with pixels.
Exactly. That's crucial. Instead of dealing with raw, high-dimensional camera images, LDP first learns to compress the visual information into a much smaller, more essential representation. This latent space captures the important stuff without all the noise.
Okay, makes sense. So how does it learn this compressed representation, this latent space?
It uses a variational autoencoder, a VAE. Think of it like a really smart compression tool specifically for the robot's visual input. It takes an image, squeezes it down into this compact latent code, like a compressed sketch of the scene, and then it tries to reconstruct the original image from just that sketch.
And the better it can reconstruct, the better the sketch captures the important details.
Pretty much. The goal is to make that latent code capture everything visually relevant for the task. And the really powerful part is, you can train this VAE using all your visual data. Expert demos, yes, but also those failed attempts, the action-free videos. The more diverse visual input it sees, the more robust that latent representation becomes. The paper mentions using a VAE objective. That VAE parameter sort of controls the trade-off between reconstruction quality and how compact or well-structured that latent space is.
Got it. So a robust visual understanding learned from diverse data. Now back to the planning part. How does it imagine the future in this latent space?
Right, so once the VAE is trained and we can get these latent sketches, LDP uses a diffusion model as the planner. This planner takes the current latent state, which includes both the visual sketch and maybe the robot's own joint positions, its proprioception, and it forecasts a whole sequence or horizon of future latent states.
Like predicting a short movie, but just using these compressed sketches.
Yeah, exactly. A movie of latent codes. And here's a key thing. This planner can learn just by observing sequences of states changing over time. It doesn't necessarily need the actions that cause those changes. That's where the action-free video data is super valuable. The planner learns the typical flow of a task visually. They use a conditional UNet architecture, which is good for this kind of sequence prediction. Equation 2 in the paper shows the objective for training this planner.
Okay, that's really interesting. So just watching is enough for the planner to learn what comes next visually, or at least in this latent representation.
Precisely. It learns the dynamics of the task in the latent space. Now, you still need actions, right? That's the second diffusion model, the inverse dynamics model, or IDM.
Right, the part that translates the plan into actual movement.
Yeah. The IDM takes two consecutive latent states from that predicted sequence, say, the state now, and the predicted state a fraction of a second later, and its job is to predict the specific robot action that bridges that gap. And this is where data that does have action labels becomes important. Even the suboptimal data is useful here because it still shows some action leading to some state change. The IDM learns that mapping. They use an MLP PresNet architecture for this IDM, trained with its own loss function, detailed in equation 3.
So just to recap the flow, VAE compresses the image. Planar diffusion model predicts a sequence of future compressed states. IDM diffusion model looks at pairs of these predicted states and outputs the actions needed.
You got it. And critically, the VAE is trained first, and then its encoder part is frozen. The planner and IDM are then trained separately, operating purely on those frozen latent embeddings.
Which makes training potentially simpler.
Potentially, yeah. And because it's all happening in this low-dimensional latent space, it avoids the huge computational cost you'd get trying to predict raw pixels or generate full videos, which some other methods attempt. That's key for real-time robot control.
Makes sense. Efficiency is always a win in robotics. So the theory sounds good, elegant even. How did they actually test it? Did it work?
They did quite extensive testing. They used simulated environments first, specifically the Robomic benchmark, tasks like lift, can, square, common manipulation challenges, also an Iloasim transfer cube task. And importantly, they designed the experiments to be in a low data regime for the expert demonstrations.
To really push the limits and see if using the other data helped.
Exactly. They wanted to highlight the benefit of adding suboptimal and action-free data when you don't have much expert data to begin with. They carefully controlled the amounts of each data type.
And who are the contenders? What baselines did they compare against?
A good range of recent methods. Diffusion policy, or DP, was a key one, since LDP also uses diffusion. But DP diffuses directly over actions. They also included variants like DP with reward conditioning, DP combined with separate representation learning, DP with pre-training and fine-tuning.
Trying different ways to boost DP's performance.
Right. And they also compared against video prediction methods, specifically UniPy, both in its open-loop and closed-loop versions. These try to predict future video frames directly.
Okay, so a solid set of comparisons. What were the headline results? Did LDP live up to the hype?
The results were pretty compelling, yeah. Across the board in simulation, LDP generally outperformed the baselines, and the advantage was most pronounced in those low expert data scenarios. It clearly showed it could effectively use action-free data, doing better than methods like DP-VPT, which try to auto-label action-free video, and it also outperformed the video planning methods like UniPy. UniPy could also use action-free data, but it seemed to struggle more with the fine-grained control needed for manipulation, and generating high-fidelity video predictions is just inherently hard.
Right, predicting exact pixels is tough. And what about the suboptimal data? Did LDP benefit from that too?
It did. That was another key finding. Vanilla diffusion policy didn't really improve much, or sometimes even got worse when suboptimal data was added. But LDP did show performance gains when incorporating that suboptimal data alongside the expert data. It could extract useful signal from those bad examples.
Which is huge because suboptimal data is often much easier to collect.
Absolutely. And when they combined both action-free and suboptimal data for LDP, that's when it really shone, achieving the strongest results overall in the simulations.
That's quite convincing in Sim. Did they manage to replicate this in the real world?
They did. They set up the Robomic lift task on a real Frankopanda arm using a wrist camera and teleoperation with an Oculus headset for data collection. They collected expert demos, some suboptimal trajectories, and some action-free video. And the results mirrored the simulation findings. LDP consistently outperformed the baseline diffusion policy on the real robot. And crucially, adding the action-free data further boosted LDP's real-world success rate. That's a really important validation point.
Definitely. Real-world robotics is the ultimate test. Did they do any ablation studies to pinpoint why LDP was working so well? Like, breaking it apart?
Yeah, they did some good ones. One interesting test was a hierarchical version of LDP. Instead of planning a dense sequence of latent states, they tried planning over more sparse, high-level subgoals. Surprisingly, maybe, that actually performed worse. It suggests that having that dense, step-by-step forecast of the latent state trajectory is really important for LDP's success. It needs that detailed plan.
So the dense prediction matters. What else?
They also tried swapping out their learned VAE Latent Space for pre-trained visual representation, specifically Dino V2 embeddings. Even when they projected Dano down to a similar low dimension,
Performance tanked.
significantly lower success rates, yeah. It really underscores the importance of learning that latent space specifically for the task and the LDP framework, rather than just using a generic visual encoder.
Okay, so the learned VAE space is key. Any other interesting ablations?
They checked if pre-training the video baseline, UniPy, on a huge external video dataset, AVDC DATO, would help it. And it didn't really make a substantial difference on their robotics tasks. It suggests that massive general video pre-training doesn't necessarily translate directly to better robotic control performance, at least not for that method, further highlighting the targeted efficiency of LDP's approach.
Right, so pulling it all together, the key seems to be this combination. The learned, compact, latent space via the VAE, and then using diffusion models within that space to separately handle the dense state forecasting planning and the action prediction, IDM.
Exactly. That modular design, operating in the learned latent space, is what allows it to effectively incorporate these diverse, non-expert data sources. The action-free video for the planner, the suboptimal demos for the IDM. And that's especially powerful when you're data limited on the expert side, which is, let's face it, very often the case.
Makes sense. Now, no paper is perfect. What limitations or future directions did the authors themselves point out?
They were quite clear about a few things. First, while the VAE latent space works well, it might not be theoretically optimal for control. The objective is image reconstruction, not directly task success. So exploring other representation learning goals could be fruitful.
Like objectives more directly tied to predicting actions or future states.
Potentially, yeah. They also acknowledge that diffusing over states, even latent states, is computationally a bit heavier than just diffusing over the typically lower dimensional action space, like standard diffusion policy does.
A trade-off for the flexibility, perhaps?
Seems like it. And for future work, the obvious next step is testing LDP on even more complex, diverse, real-world tasks, especially using data that might be collected autonomously by robots, or maybe less structured human data. They also mentioned keeping an eye on rapid advancements in diffusion models themselves. Maybe newer architectures or techniques could plug into the LDP framework for even better performance.
Okay, so wrapping up, the big picture here is that latent diffusion planning looks like a really promising path forward for imitation learning. By smartly separating planning and control and doing it all within a learned latent space, it opens the door to using way more kinds of data than just those perfect, expensive expert demos.
Right. It potentially lowers the barrier to training capable robots by letting us leverage data that's often easier and cheaper to get failed attempts, passive observations.
Which could really accelerate progress in getting robots to handle more complex tasks out in the real world.
Definitely. And it makes you think, doesn't it? If robots can learn effectively from just watching or from trial and error data that isn't perfect, how does that change how we should even think about collecting data for robot learning in the future?
That's a great question to ponder. Maybe it's less about perfect imitation and more about providing diverse experiences. Something to chew on. Thanks for breaking down this paper with us today.
My pleasure. Really interesting work.
Absolutely. We'll be back soon with another AI Paper podcast. Thanks for listening.